So, welcome you back. So, today we'll discuss on a problem where we again have a very nice structure, and which is the case where we are dealing with location scale family of distributions. So, what we were doing so far is we were trying to look for a nice structure in the problem in terms of whether the given problem is invariant or not. If it so happens, then it suffices to consider only invariant decision rules or invariant estimators. So, that reduces the class of estimators under consideration. An advantage of that is once your class of estimators is restricted, it is possible to find the best estimator within this restricted class in many situations. So, the first thing which we did was for the location family of distributions, we saw that location family of distributions is invariant under additive group of transformations. So, we applied the invariance theory to reduce the class of estimators under consideration, and then we saw that we can find a best estimator within that class. And reason for doing that was because the risk of any invariant estimator was not depending on the parameter. The risk was constant. So, it was possible to find the estimator for which that constant risk is minimum. You see, generally the problem is because risk function is a function of parameter. So, finding an estimator which minimizes the risk at every parametric point becomes a difficult. But by imposing the invariance, which is possible when your estimation problem has a nice structure, the risk function of any invariant decision rule turns out to be constant, at least in some situations. In the location family model, we saw that that was the case. In the scale family, we saw that that was the case. Now, what I'll do is I'll see whether invariance principle can be applied to the location scale family of distributions. So, for that, let us try to see the model. So, what I have is I have a data or a random vector x1, x2, xn. This has a distribution function f, which belongs to parametric family of f thetas. Now, here theta is a vector. It has two parameters. One is a location parameter and one is a scale parameter. So, mu sigma, which belongs to mu is a location parameter, so it can be anything in the real line. Sigma is a scale parameter, so it can be anything in 0 to infinity. So, this is the family of distributions where f theta of x1, x2, xn is same as f of x1 minus mu by sigma, xn minus mu by sigma, by this x, which is x1, x2, xn, this belongs to Rn, theta, which is mu sigma, belongs to cross 0 to infinity. So, let me take my theta, which is R cross 0 to infinity. This is my parametric space, right, because your theta is taking value in this space. So, this is parametric space. Now, here f is a specified PDF. So, I completely know what my f is. For example, in the case of normal, it could be product I is equal to 1 to n, 1 by root 2 pi e to power minus xi square by 2. So, that means this model covers the case where you have observations x1, x2, xn, which are IID, normal, with mean as mu and variance as sigma square. Of course, this covers much more general scenario because here the observations may be dependent as well. Okay. So, now let f is the PDF of capital F or the PDF corresponding to capital F, then the PDF of x is, when theta is a true parameter, is f theta of x1, x2, xn, which is 1 by sigma to power n. So which is basically taking partial derivatives of this with respect to x1, x2, xn. 1 by sigma to power n, f of x1 minus mu by sigma. Because this small f was the distribution, was a PDF corresponding to capital F. Standard thing, right? Now I have to look at what is the suitable group of transformations under which I remain inside the same family P. So in the location case, we saw that suitable transformation was x1 plus c. In the scale case, we saw that it was b of xi's. So in this case, it suggests that I should have g bar as collection of all those BC's, such that B is positive, C is in R. So this is my group of transformations, where G bar BC of x1, x2, xn is nothing but bx1 plus c, bxn plus c. X belongs to Rn, B positive, C is in R. Now it is straightforward to see that distribution remains invariant. For example, you can see PDF of, what is a PDF of y1, y2, yn, which is basically applying this transformation, right? Which is, let us say, bx1 plus c, bxn plus c s. So I have to get PDF from here. So what is a PDF? So I have to, what is the transformation here? yi is nothing but bxi plus c. So I'm finding the PDF at the small point y1, y2, yn. So I have to make the transformation yi is equal to bxi plus c. So that means xi is nothing but yi minus c by b. I is equal to 1 to n. Jacobian, you can see it would be a diagonal thing because xi is only related to yi, no other y's. So it would be diagonal element 1 by b, 1 by b, 1 by b. So Jacobian turns out to be 1 by b to power n. So joint PDF of this is nothing but 1 by sigma to power n, it remains as it is. F of, in place of xi, I have to write down yi minus c by b. So y1 minus c by b minus mu by sigma, so on. Yn minus c by b minus mu by sigma, which is nothing but, and then the Jacobian part. Jacobian would be with a modulus sign, but b is positive. So it will be 1 upon mod of b to power n, which will be same as 1 by b to power n. If you want, you can write down mod of b to power n, but b is positive, so it would be. So this becomes 1 by b sigma to power n, f of y1 minus b mu plus c by b sigma, yn minus b mu plus c by b sigma. So if I apply the transformation bx1 plus c to bxn plus c, I get this PDF. Only thing I have to see whether this belongs to the same family or not. For to be in the same family, 1 by sigma to power n, so it is okay in place of sigma, except that b sigma has come. The only thing I have to make sure is b sigma is positive. B is positive, sigma was anyway positive, so b sigma is positive. F of y1 minus some mu divided by whatever sigma was here. So sigma was here, so b sigma, that is okay. Then b mu plus c. So mu becomes b mu plus c. So again, you are in the same family because mu was in R, so b mu plus c is also in R. So what you have is mu sigma gets transformed to B mu plus C and B sigma. Again, you are in the same family. Now let me note a word of caution over here, that if this family was such that my mu was also greater than or equal to 0. So suppose I have a prior information that mu is greater than or equal to 0. Now when I apply this problem, my mu gets converted to B mu plus C. Now this B mu plus C greater than or equal to 0, I do not know, because C can be anything in R. So B mu plus C can be negative also. So in this case, the problem will not be invariant under this group of transformations. If one has to do that, possibly one has to take C greater than 0. C greater than or equal to 0. And then one has to see whether it's a proper group of transformations or not. But at least, if mu was given to be greater than or equal to 0, the problem, the family of distributions P is not invariant under this, because C is in R, so B mu plus C can be negative also. Okay, so what you get is my P is invariant. So this suggests that P is invariant under G. And what is the induced group of transformations? Induced group of transformation is given by S. All right. So with induced group of transformations on my parametric space theta as G bar, which is nothing but G bar of BC, B positive, C is in R. And what should be my G bar BC of mu sigma? This comes from here. Mu becomes B mu plus C, and sigma becomes B sigma. So and B sigma. Mu and sigma belongs to theta. B positive, C belongs to R. So my family of distributions is invariant. Now, here there are two parameters, mu and sigma. So I can talk about estimation of sigma to power R and estimation of mu. So let us consider these two problems separately.